So let's look at a base buffer example. The only difference here is that a basic buffer is going to buffer on the basic end of the pH range. So here's an equation. We have a base in water forming a conjugate of that weak base and hydroxide ions. So let's think about what happens if a strong acid is added. Well, if a strong acid is added, then this base, NH3, can accept protons from the incoming acid and make more NH4+, thereby removing the strong acid from the solution and neutralizing the pH. If, on the other hand, a strong base is added, NH4+ or ammonium ions can donate the proton, forming its conjugate base and water, and again, the pH remains about the same. So the base and its conjugate acid can both react, neutralizing the pH. So in the base buffer acid, a weak base, B, will accept protons supplied by the strong acid, removing the strong acid from the solution. The conjugate acid of that weak base, which again would be a weak acid, can transfer protons to the hydroxide ions added by the strong base, again neutralizing the effect there. So a buffer is a mixture of a weak acid-base conjugate pair that will stabilize the pH, serving as a source or a sink for the added protons. So that's how a buffer works. So I mentioned buffering is very important. It's very important in your blood. Your blood is buffered in the range of pH 7.35 to 7.45, and you have a buffering pair and a conjugate acid-base pair that's in your blood that does the work. So nature has its own buffering system designed to keep the pH of your blood constant.